Hello, I am George Heath, owner of Continental Pump Company. The purpose of this video is to inform you of our products, tools, and basic information on how to select a pump. Our goal is to offer quality products and services at a competitive price, along with our commitment to help you, our valued distributor. You will find that our progressive cavity pumps are very versatile as they can be used in a variety of applications and industries. Between our pumps, additional features, and services, we can make a pump specifically for your needs. Again, thank you for being a Continental Pump distributor and enjoy the video.
Progressive cavity pumps have similar characteristics to rotary or reciprocating pumps such as piston, diaphragm, lobe, and screw pumps, with the one common feature of sealed cavities and operational similarities, like being able to pump at extremely low rates to even high pressures. The similarity between other pumps and progressive cavity pumps generally ends there. Of all types of pumps available, progressive cavity pumps are able to handle a wider range of fluid viscosities and properties than any other type of pump. The unique design of the pump makes them useful for a variety of pumping applications such as transferring and metering while handling shear, sensitive, abrasive, and viscous fluids.
Continental pumps are identified by model number, frame size, and material type. The model number nomenclature depends on the materials used in the pumps, which are based on the types of fluids to be handled. The first number indicates the number of stages for the rotor and stator. The second letter indicates the pump models such as CL, CM, or CG. The third number indicates the size of the rotor and stator and pump frame size. The fourth indicates the pump body casting material. The fifth indicates the rotor and internal parts material, and the sixth indicates the stator material.
Our rigid stator pump line consists of our CL, CM, and CG models. Based on your piping situation, the suction housing can be rotated from 90 degrees to 270 degrees upon request. The CL model is suitable for a wide variety of applications and are the most frequently used. When properly applied, they give excellent long life performance at the most economical cost. The CM model is similar to the CL model except has a larger drive head to handle the increased horsepower that is needed to produce the higher pressures that can be developed by these pumps. Our crown gear joint pumps consist of our CG model. This model's suction housing can also be rotated from 90 degrees to 270 degrees upon request. The CG model is designed to handle the heavier applications of sewage, industrial waste, polluted liquids and slurries. Incorporated into this more rugged pump is a drivetrain using crown gear joint connections to the rotor and drive shaft.
Our wobble stator pump line consists of our CP, CPM, and CPML models.
These models are available with horizontal or vertical suctions based on your piping or space limitations. The CP model, also known as the bare shaft pump, operates with low costs and are compact, making them ideal for light-duty use. The CPM model is similar to the CP model, except it is a closed-coupled type pump that is driven by a Continental spec motor that is directly bolted to the pump. The CPML model is similar to the CPM model, except it is driven by a standard motor attached by a specific motor coupling for different drive arrangements.
We offer a variety of options for our pumps, such as vertical and rotated suctions. They are used if the piping is different and our normal horizontal pumps are not needed. The vertical suction is available for our CP, CPM, and CPML models, and the rotated suction is available for our CL, CM, and CG models. Close coupled is an option when both a pump and motor are needed. This combines the pump and motor together. A V-belt is a pulley-type system that is driven by electric or gas motors. A gas engine is an option when a portable unit is needed. We offer hydraulic adapter units when hydraulics are the source of power to drive the pump. The complete base job unit includes pump, gearbox, motor, and steel base, which we can build to your particular specifications. A gearbox is required to control the maximum RPM of the pump. It also provides added torque at low startup speeds. VFD, or variable frequency drives, is an option to control the pump at various speeds. The most common types of motors are general purpose, explosion proof, inverter duty, severe duty, wash down, and single or three-phase. Contact us for more types that are available.
The reason progressive cavity pumps are used are because they are durable with only one moving part, rated for longevity. In operation, our pumps are primarily a fixed flow rate pump and offer long life and reliable service, transporting thick, viscous fluids. Abrasive fluids can shorten the life of a stator, but by slowing down the RPMs, this will help reduce the wear. Slurries can also be pumped reliably as long as the slurry is viscous enough to maintain a lubrication layer around the particles and protect the stator. The combination of the rotating rotor and the core of the stator result in a series of sealed cavities that progress from the inlet to the outlet, either due to pressure or gravity. As one cavity is opening, another is closing at the same rate, so the quantity going through both discharge and suction are continuous. The result has a non-agitating flow without the use of valves. So this makes progressive cavity ideal for metering or other applications where predictable flow rates are required. At the points where the rotor touches the stator, the surfaces are generally traveling diagonally, so these areas need to be lubricated by the fluid being pumped. This means that more torque is required for starting. Rapid deterioration of the stator can happen as a result of the pump operating without fluid. This is also called run dry. The various materials used in the manufacturing of Continental pumps allows our pumps to handle almost any fluid. If it will push through pipe, you can pump it with Continental progressive cavity pumps. Whether it be acidic, abrasive, or viscous, we can help you with your application needs. Some of the examples that progressive cavity pumps can help you with are latex, polymer, brine, asphalt, tar, drilling mud, varnish, shellac, pulps, and numerous oils such as castor, vegetable, linseed, and soybean. You can visit our website for a list of more types.
Progressive cavity pumps have two key components which help move the fluid. They are the rotor and stator. The rotors are made of hardened steel or stainless steel and are covered with a chrome plating to gain resistant to corrosive and abrasive materials. Some types of liquid affect the chrome plating. In those applications, a non-plated rotor should be used. The stators are metal tubes with internally molded cavities of either synthetic or natural rubber. The rotor seals tightly against the flexible rubber inside of the stator as it rotates, forming tightly sealed cavities which carry the liquid towards the discharge port. The liquid does not change in shape or size when pumped due to the tightly sealed cavities. The effect of the progressive cavity design is that the fluid is moved at a very predictable and steady rate. Positive displacement of the pump starts the instant the rotor turns. The liquid acts as a lubricant between the pumping elements and should not run dry. Understanding the pump terminology helps to select the best performing Continental progressive cavity pump to fit your needs. Here are a few things you should know. The capacity or volume is the rate of flow typically measured in gallons per minute or GPM. Pressure is determined by how much is required to move the liquid that is being pumped through the piping system and the kind of liquid that is being handled. The difference between the pressure required at the pump discharge and the pressure being introduced into the pump suction is the differential pressure and is expressed in pounds per square inch, or PSI. Viscosity is the resistance to flow as expressed by various scales of measurement. However, the most commonly used is centipoise. The viscosity usually changes with temperature and should always be considered. Temperature refers to the maximum and minimum temperatures at which the fluid is to be pumped. This is a highly important factor in pump selection. High temperatures can cause distortion and swelling of the stator materials, and low temperatures can affect viscosity that reflects in flow characteristics and horsepower requirements. Operating time, or the operating cycle of the pump, should also be considered. Whether the pump is to run continuously or intermittently can be a factor in the selection of the drive. Corrosion, whether the fluid being pumped is neutral, acidic, or alkaline, should be considered when selecting the proper materials of pump construction. The pH value of the fluid should also be known or determined. A pH of 7 is neutral, below 7 is acidic, and above 7 is alkaline. The abrasive properties of the fluid to be pumped should be classified. Abrasives can look alike and appear to have similar properties. However, they can wear differently. You must classify the fluid in order to select the proper pump construction and operating speed. These 4 classifications will serve as a guide and help in the determination of the necessary materials needed for the pump construction. No abrasives, including clear water, gasoline, fuel oil, and lubricating oil. Light abrasives, including dirty water containing silt and/or small amounts of sand or earth. Medium abrasives, including clay slurries, potter's glazes, porcelain enamels, frit, sludge, and wood dust and water. Heavy abrasives, including slurries containing large amounts of sand, emery dust, lapping compounds, mill scale, plaster, grout, and roof gypsum.
Continental progressive cavity pumps have been time tested with proven unique characteristics that excels in performance unlike other types of pumps. They are built of various materials and many sizes with capacities of less than 1 gallon a minute to over 400 gallons a minute and pressures up to 450 psi. There are 7 key advantages to our pumps, the first being positive displacement. This occurs at the turning of the rotor, which develops a positive pumping action similar to a piston moving through a cylinder. The pump pressure developed does not depend upon the speed of the rotating rotor. The capacity of the pump, the approximate viscosity, and the pressure can be projected for particular operating conditions. The second advantage is uniform discharge flow. Fluids are uniformly discharged without pulsation in a constant, steady flow. Displacement remains the same with each revolution of the rotor, permitting accurate and predictable metering relative to the fluid being pumped. Because of the unique flow characteristics, these pumps are well suited for low shear applications. The third advantage is when the pump is in process, all fluids are pumped with a minimum amount of turbulence, agitation, pulsation, or separation disturbance. The fourth key advantage would be the self-priming. Pumping action starts at the time the rotor is turned and is capable of 28 feet of suction lift based on water in an appropriate installation. The liquid being pumped acts as a lubricant between the rotor and stator and forms a continuous seal to create good suction and discharge capabilities. The fifth key advantage is solids in suspension. Solid particles over a wide range of size and shape, as large as 1.1 in diameter, are pumped with no difficulty. Our sixth key advantage is reversibility. Our pumps can be operated clockwise or counterclockwise with effective performance in most installations. Contact us to see your application is suitable for reverse operation. Our seventh key advantage is installation. Our pumps can be purchased separately or built into complete units. These units can be mounted on welded steel bases with specified couplings, are belt guards, and can either be driven by flexible couplings, V-belts, gearbox reducers, or hydraulic motor adapters. If variable speed drives are needed, the units can be driven by either electric motors, gasoline engines, diesel engines, or air motors. Our pumps can be mounted horizontally or vertically, and the suction port can be rotated to any position for appropriate entry of the fluid.
Alright, today we're going to talk about the pump application data sheet. This is going to allow us to select the proper model that we need for our pump application. So what we're going to do is we're going to go to the chart for the pump application data sheet, and on the far left hand side we're going to be looking at the CL model. Now as we come across to the right, you'll notice that we can pump 0.9 to 400 gallons a minute up to 225 psi. And if we slide all the way over, you'll be able to check at that point what type of frame size is offered in that particular L frame. All right, now we're going to go down to the CM model pump. Now the CM is generally used for applications where there's a higher PSI rating needed for that particular situation or application. So in the CM model, you can see that it can do from 0.1 to 24 gallons a minute. So our flow has gone down, our pressure is going to go up, and it's capable of doing 450 psi. And over to the right, you can see that there's the 4 options that you would have in the frame size for that particular selection. Now we'll drop down to the CG model pump. Now the CG model pump is generally used for heavier applications, wastewater treatment plants, things of that nature. And it's going to be able to do a higher volume, but the pressure is going to go down. So this pump is capable of doing 3 gallons a minute up to 400 gallons a minute. And over to the right, once again, you'll notice the frame sizes that are available for the CG model pump. We're going to go to table 1, and here we're going to be able to select what frame size the pump is able to handle, what size foreign material which be flowing through the product. So what we're going to do is we're going to drop down to the far left hand corner of table 1 where it says maximum particle size. We're going to slide over to the 0.40 inches, and right there you're going to see the minimum frame size. Available for that material size is a CL6. So that's how you will designate the model frame size that you would need for foreign materials. So now we're going to jump over to table 2, and here we're going to talk about the viscosity and how the viscosity is going to change or regulate the speed and flow of our pump. So what we're going to do, for an example, we're going to go to the pump frame size, which is on the left hand side. We're going to slide down and we're going to select where it states 1 CL6 through 3 CL6. And we're going to just slide right over to where the viscosity, up in the upper right hand corner, it says viscosity in centipoids. And then we're going to go to where it says 1 to 1000, and we're going to slide down to the L6, and you're going to see there that the maximum RPM that pump can run at that viscosity is 900 RPMs. The maximum flow you're going to get is 47 gallons a minute. And real quick for the example, we're going to slide right over to back up to the top where it says 5,000 to 10,000 centipoids. Then we're going to slide right back down to the L6 again, and you will see there, because of the thickness of the product, we got to slow the pump down. So now we're running at 250 RPMs with a maximum flow of 13 gallons a minute. So that is how you're going to use your viscosity chart when selecting your pump frame size. It's very important. Okay, now we're going to travel over to table 3, and here we're going to talk about how the abrasive characteristics can affect your pump selection as well. So what we're going to do is we're going to go down on the far left hand side. We're going to once again use the CL6 model for the example. So under pump frame size, we're going to slide down to the 1CL6 through the 3CL6, and we're going to come over, and if you look at the upper right hand corner, it says abrasive characteristics, and underneath that it says none, light, medium, and heavy. What we're going to do is we're going to select none. We're going to follow that down to where the CL6 model is, and where those intersect, you're going to see that the maximum flow rate is 47 gallons a minute. Your maximum RPM is 900 RPMs. So that's with no abrasive characteristics in your product. So now what we're going to do, just jump right over to the heavy, and then where those two intersect, you're going to notice real quick that our maximum RPM is really dropped down from 900 to 225, and our flow went from 47 gallons a minute down to 12. So it's very important that we understand how the abrasive characteristics can affect our pump selection. Now we're going to jump over to table 4, and here we're going to talk about how the abrasive characteristics can affect our pressure as well. So this one will be real quick to go over. We're going to go over to the left hand side, pump frame size, where it's got the 1 and the 2, and we're going to slide over to the right where it says none. So there's no abrasive characteristics there. That pump can pump 60 PSI. So if we're going to slide back all the way over to heavy for the example, and we're in still the same frame size, and you can notice it went from 60 down to 10 due to the fact of the abrasive characteristics. So it's going to affect our pressure as well. So now we're going to jump down and we're going to go through the 3 through the 12, which is our most common L-frame pump models that we use. So what we're going to do is we're going to go over to the right, and there's no abrasive characteristics in there. You can see that we can pump up to 75 PSI. Now if we slide all the way over to heavy again, you will notice it goes from 75 PSI to 15 PSI. So once again, it's very important to understand that when you're applying that to your application. The next step what we're going to do is we're going to discuss how to use the performance data sheet. And when we do that, I'm basically going to put together a sample, and then we're going to use that sample and walk you through the chart to help you select the proper pump for your application. So what we're going to do here is we're going to use an example is going to be, we have an application where the pump needs to be pumping 50 gallons a minute at 100 PSI with 5,000 centipoids, which is the thickness of the product. So what we're going to do is we're going to use this chart, and we can very quickly find out how many gallons a minute that each individual pump can pump to get us right in range very quickly. So we'll go up to the upper right hand corner where it says 1200 RPMs, and right underneath that it's got the GPM. So what we're going to do is slide down that column there, and you will see that the maximum gallons per minute that within that column is 24 gallons a minute. And if we look over to the left, you'll see that's a 3CL4. We already know that's not big enough because we need 50 gallons a minute. So let's go back up to the top, and we'll go over to 900 RPMs. And then we'll go under the GPM again, we'll slide that down, and we'll come down, we're like a 1CL6, it's 47 gallons a minute. That's just a little shy. So we'll continue on down that line, and we'll come to 100 gallons a minute. And that's going to be at an L8 frame size. So we know that that is within our range. So let's focus on going to a L8 frame size. Now we got to figure out our PSI. So to do that, let's go over to the upper left hand side here. You'll see that it's got gallons per minute per 100 revolutions, and then right to the right of that it says pump speed with pressure, PSI. We're going to use that column there to get us in the right range. So what we're going to do is slide down to the CL8, and you'll see one here, it says a 1CL8. Maximum pressure is 75 PSI. So that tells us right there, that pump there is not big enough to do what we need to do. So what we're going to need to do is step up to the next stage. And now each stage is capable of doing 75 PSI, which we talked about just a little while ago. So real quickly, we already know that 2CL8 is going to put us within that range, up to 150 PSI. Alright, so we're going over back to table 2. And at table 2, we're going to be able to take our viscosity and find out how it's going to suit with our application that we're trying to apply this to. So what we're going to do is we're going to go up to the far left-hand corner of our chart where it says pump and frame size, and we're going to slide down where it's got the 1CL8 through the 3CL8. And then what we're going to do, so we got where that's at, so you go up to the far right-hand corner and it says viscosity in centipoids. So what we want to look at is at 2,500 to 5,000 centipoids. Seeing how our product is at 5,000 centipoids, this is very important. So what we're going to do is we're going to slide down there, and you can see very quickly that the maximum RPM that we're going to be able to run this pump at is 450 RPMs. And the maximum flow for that is going to be 53 gallons a minute. So we're right on the borderline of getting our gallons per minute, but technically this should still work. So what we're going to do is we're going to get our performance data sheet, which is going to be our pump curve. And what you'll notice is on the left hand side is going to be your gallons per minute, and on the bottom is going to be your pressure. So what we're going to do on the left hand side, at the bottom left hand corner, you can see it's 0. So we're going to take that up to 50, and then at the bottom left hand corner, and we're going to take that to the right, that's going to be your PSI, and we're going to slide that over to 100. So it's 50 gallons, 100 PSI. And all we're going to do is we're going to come up and we're going to intersect where those 2 points meet. That is going to give us our RPM of that pump. So when we do that, we're going to find out real quick that this pump has to be pumping at 500 RPMs to achieve the 50 gallons a minute at 100 PSI. So right away, here from the start, we thought a 2CL8 was the proper pump for this application. But by using the charts and the information that we provided, you find out real quick that this is not going to work. So what we're going to have to do is go up to the next pump size, and that's going to be a 2CL10. And we're basically going to do the exact same thing. So what we're going to do is we're going to come over to the left-hand side of your graph, and you're going to notice that that's your gallons per minute. At the bottom left, you're going to take that up to 50 gallons a minute, and at your bottom left corner, you're going to slide that over to the right, over to 100 PSI. Once again, we're going to slide those up and across, and where those 2 points intersect, we're going to find out that that is at about 350 RPMs. So right there, that's telling us that we're going to be within our 450 RPMs because of our viscosity. So this pump here is going to be capable of doing the job that we're looking for it to do. Okay, now that we've come to the conclusion that we're going to be using a 2CL10 to achieve the job that we were after, which is 50 gallons a minute, 100 PSI at 5,000 centipoids. So what we need to do now is size up the motor size for that unit. And to do that, we're still going to use the performance data sheet, which is your pump curve. So all that's going to be done is by going to the right hand side of our pump curve, and you will notice that it states over there horsepower. All right. So as you will see in the graph, on the right hand side where it's got an HP and then it's got 700, 600, 500, continuing on down to 100 RPMs. Okay, and those lines are going diagonally across the graph. Those are the graphs, or those are the lines that we're going to use to calculate our horsepower rating. So we already know that we're running at 350 RPMs. So what we got to do, underneath that HP, where it's got the 765, 400, we're going to come right down to that. So where it's 350 RPMs, now we're going to slide down that diagonal line to where it meets our 100 PSI for our application. So when we do that, those are going to intersect. Then we go straight over to the right hand side, and that'll be at the bottom right corner where it says 0, 4, 8, 12, 16 and on up. When we slide straight over there, you're going to see that we're going to be coming out at about 6 horsepower is what it's going to be coming out to, which they don't have 6. So obviously we're going to be going up to say 7.5 horsepower. It's always important to remember with a progressive cavity pump that you need to bump up in your horsepower rating. We need to bump this up to the next size up, which is going to be the 7.5 horsepower, due to the fact that the starting torque rating on a progressive cavity pump is always going to be higher. So for this particular application, we're going to need the 7.5 horsepower motor. And as we came to the total conclusion, we're at a 2CL10, which is going to give us our 100 PSI, 50 gallons a minute, with our 5,000 centipoids, with the 7.5 horsepower motor.
Hopefully this video has been beneficial and informative to you, and we look forward to Continental Pumps supplying you with all your pump needs.